I will start the session. So yeah, my name is Manuel. I'm a PhD candidate at the Stuttgart Media University and University of Tübingen, and I primarily focus on using program synthesis for explainable reinforcement learning. And in this talk, I will start with what is explainable reinforcement learning. So maybe that's the reason why I'm the first here, because I prepared some slides for it. And then I explain why I choose program synthesis, why I think that programs are the best representation for this. And then I will outline a research idea I have, how I can use these methods to apply them to explain board game strategies. Working. No. Okay. So yeah, what is explainable RL? And we can differentiate explainable RL into intrinsic and post-hoc methods. And intrinsic methods are interpretable because the model is understandable. It's like having a small decision tree to play the game, or having a program which you can analyze and interpret. And post-hoc explainability is if you have an additional model to your own model, which explains the decision. And I think in supervised learning, the most famous one is GradCam, where you generate a heat map, a saliency map of the model activations. And then you have this heat map, which should show you which region in the picture was responsible for making the decision. And then in reinforcement learning, the explanations also differ how local they are. Do you have a global explanation which can explain the whole policy over time as well? Or do you have only a local explanation where the explanation is only generated in the immediate context of the state of the action? So it is only dependent on the current state or on the current last two states or so. And we have also other categories, how algorithmically complex they are, how expressive they are, and is this method portable to many different environments, or is it only useful for this only given environment? So, and how can we explain decisions? We can calculate feature importance score. We can have textual justifications from an additional model or using a language model for this. We can find important states and transitions. We can generate saliency maps, or we use interpretable agents, which are represented as programs that can be rule-based, mathematical expressions, logic, or tree-based. So then the next question is, can we trust the explanation? So there was a paper from last year which analyzed this for supervised learning, and they had in the conclusion, our paper demonstrates that in adversarial context, local post-hoc explanations are of very limited use. From a technical and philosophical point of view, these explanations can never reveal the unique true reason why an algorithm came to a certain decision. In complicated black box models, such a true reason simply does not exist. So, and they defined adversarial context for when the model and the explainer have a different incentive in mind. So if you have a model which should predict if a customer for a bank receives a loan or not, and the customer wants to have the loan, but the model denies it, then you have an adversarial context. And they say that post-hoc explanations are good if the model and the explainer have the same goal in mind, like in medical imaging, where the doctor and the patient want that the patient will be healed. And so the question is, can we transfer this to reinforcement learning? And if yes, then would be games will be a game every time in adversarial context, because in chess you have like two players who play against each other. And then with this conclusion, then the post-hoc explanations wouldn't be good at all. And then you could only use post-hoc explanations like for cooperative games with like Hanabi or so. And on the right, there's another paper from 2020, which is called Sanity Checks for Saliency Metrics. And there they have like 4 saliency methods for explaining the same classifier for the image on the right and on the left. And on the right is the Sobel edge detection, which is just a computer vision algorithm, which they say should serve as a baseline. And all saliency maps highlight different regions on the map. So this is for me also a clear indication that saliency maps are not really useful if every method explains something different for the same classifier. Yeah, and that's the reason why I choose to work with programmatic policies, and programmatic policies are reinforcement learning policies represented as programs. And the benefits are that programs are inherently interpretable. You can study them before using them. They are verifiable before using them in production. You can edit them by software engineers, and they also easily extrapolate to large environments. You don't need to retrain a neural network or so. You can just use the program on bigger environments. And this was, for example, a NeurIPS paper where they showed this, that they found programs for a small environment, which was 10 times 10. And they also worked on environments with 100 times hundreds. And on the right, they showed that if a software engineer is doing like 3 or 5 edits, the reward was in the end much higher. So for example, they had here, for this environment, they could, with 3 edits, could increase the reward by 0.5. And this is also a quite cool paper where they used a combination of logical feature detector programs to play very simple grid-based games. And there they have like a domain-specific language where they have like, which they call feature detectors, to combine them afterwards logically. So you could have like a cell which looks on the bottom right, and then it can perceive the environment, and then you just look for logical combinations. So what they did is like they they make the search feasible, because most of the times you cannot find programs for reinforcement because it's too hard, but they had like a nice inductive prior inside the method to make this possible for small grid games. And this is also quite cool, which I think is the only paper which did it for more complicated environments, where they learned programs for a real-time strategy game called MicroRTS, and they analyzed it with programs from humans, and they were almost equal from the performance. And here are the first 2 are programs from the local search algorithm, and the other 2 are programs written by humans. But what I think the problem here in this paper, for example, is that they really have high-level functions like harvest, attack, distance, enemy, where they already put in much prior knowledge from the human, which is put inside. So this method is only applicable for this game, for this environment. And I also want to have like a method which you can use for all board games, that you put in as only all the necessary knowledge you have, like the fundamental building blocks, like getting something on a grid, then the objects you can have on a grid, and all the rest should be learned from the data. So you shouldn't put in that much prior knowledge, where a function is doing like 10 steps if you won't have this function. Yeah, and this was actually the paper where we had in the first session as well. And I also found this pretty cool because it has something, the same ideas what I wanted to do. They generate a library of reusable functions with the language model, and they use GPT-4. And I was like, oh, cool, they could craft the diamond pickaxe from Minecraft. But in the end, then I was looking up the paper, what they did. And then I found out that they used GPT-4 and that they synthesize programs with this library. And this library is used by 26,000 people. So there's a lot of prior knowledge already on the internet available. And then it's like, okay, it's not that impressive anymore because they have a lot of programs in this training data. And I was like, what would you do if you don't have this training data available? If you cannot like write these programs to train a language model your own, like 26,000 programs of it. And this is the reason why I brought up a method last year at 8, where you build up a library of concepts the agent has learned by analyzing programs and then extract functions, extending the domain-specific language. And there you could show that with this library, that program search was much easier. Instead of synthesizing 13 lines of code, you could just synthesize in the end 1 line of code where you fill out the parameters, and then the program search was much faster. And if you then have this program which can explain the decisions of the agent, you can just execute the program and then analyze which grid cells the agent looks at. And then you get an explanation of why the agent is going forward or going to the left or to the right. So this was for the maze running environment here. And in the end, I had like functions where if there was a wall object in front of me, the agent is moving to the left, otherwise it moves to the right. And you could synthesize this program only with 2 building blocks instead of using 10 or more. So, and how I want to apply this to board games is like a combination of Dennis, Eric's, and Matthew's paper on spatial state action features, where where the agent, instead of that the agent is looking at each cell individually, you can look at, for example, on for this tic-tac-toe game, you can look at one high-level feature which represents all grid cells in the middle line. So you have like one feature instead of 3 single features, and the same is on the right. And my plan was then to first learn a domain-specific language, which is which learns the high-level features, and then when I have these high-level features, I can then afterwards, when I imitated all them and have them in my domain-specific language, I can then imitate the game traces from the game, because this should reduce the problem significantly when I restrict the search to certain areas of the search space. So my hope is that the full program search is like this big, and when I use the spatial state action features, I can make it a bit smaller, and through library learning, it will get again smaller, and in the end, I have like the correct programs. So yeah, that's my idea about it. And yeah, and my requirements are in the end that I want to have an interpretable agent, which is intrinsic explainable and provides global explanations for the same whole policy. Yeah, that I want to reduce the search space by structuring it, and that I only want to include only the necessary domain knowledge, which covers a lot of games, by just having the fundamental building blocks to synthesize programs, and all the rest should be done by library learning in combination with program search. Yeah.